Good afternoon and welcome back to the afternoon session. It is my great pleasure to introduce Professor Dr. Siddhartha Mishra from ETH Zurich. Mm, After finishing his bachelor's from Utkal University in 2000, he joined IIC TIFR joint program and he received his PhD in 2005 under the supervision of Professor Adimurti. He was a postdoctoral researcher from 2005 to 2009 at the Center of Mathematics for Applications at the University of Oslo. From 2009 to 2011, he was an associate professor at ETH Zurich. He became an associate professor in 2012 and a full professor in 2015. Professor Mishra is the director of computational sciences, Zurich, and a core faculty at the ETH AI Center. So he has received many awards, including ERC Starting Grant, ERC Consolidator Grant, Richard von Mises Prize, Jacques-Louis Lyons Medal, ICIM Colars Prize, and Infosys Prize in Mathematical Sciences. He has been also an invited speaker at many leading international conferences, including the ICIM 2018 at Rio de Janeiro. And today he is going to talk about on statistical solutions of fluid and their computation.
Okay. Thank you, Debayan. Thank you for the kind introduction. And I take this opportunity to first thank Ujjwal and all the organizers for inviting me. It's a pity that I can't be there in person. It's difficult to travel during our teaching semester. So that's my first apology. So, and the second one is that I know that the focus of this workshop is on analysis, whereas I'm not an analyst per se. I'm more from scientific computing and numerical analysis. So the talk will be a little bit different from most of the talks that you are going to see, I think. But let's see. So the question is, what does a computational mathematician? That's how I define myself. What do we do? So what we do is something can be sort of encapsulated like this, that if you have a PDE, for instance, one of the PDEs that you're going to hear a lot about, the incompressible Euler equations, which is written here. And if you've been given a domain and some boundary conditions, for instance, let's take for simplicity the unit cube, and let's take periodic boundary conditions. And then if you have some initial conditions, like for instance, the well-known what is called the Taylor-Green vortex, right? So in some sense, the problem is completely specified. You have the equations, you have the boundary conditions, the domain, the initial conditions. And then, of course, the question is compute the solution, right? That's my task. It's sort of, I cannot say whether solutions exist, unique, what are the properties and so on, but it's essential to actually compute them. So how do we do this? We have to use a numerical method. This is what we know. We have to use something which is computational, which can be used on a computer. And the numerical method that I'm going to talk about, at least for quite a bit as an example, so what I call spectral viscosity methods, spectral methods. Right. So the idea is very simple, that instead of having arbitrary L2 functions, you just expand them in a Fourier basis and to take a Fourier projection onto a finite number of modes so that you can put things on a computer. So this is just a representation of the various sort of constituents of this Fourier basis. And because we are looking for divergence-free fields, we have to do a divergence projection or divergence-free projection, and this is how the truncation happens, right? So instead of taking the Euler equations, I just take the equations in Fourier space, use this divergence-free projection, and then I get, for the time derivative, this is the term that I get. Nonlinearity, of course, is processed in some special way, but I don't have to explain this. And to stabilize my computation, I need to put in some numerical viscosity, something called spectral viscosity, which is due to Ethan Tadmor essentially. And the idea is just to put viscosity on the high modes, so that the low modes there's no need for any stabilization. The high modes, for instance, at the scale of roughly the square root of the total number of modes, you put some spectral viscosity. And this is a well-known method. It has been around since the 1980s. And we take this equation, we take these methods, we take these initial conditions, and then we compute the solution. And maybe I can show you how the solutions look like. I have a movie here. So what you're seeing is the vorticity, or the norm of the vorticity, the absolute value of the vorticity at a certain resolution, and how it evolves in time. So let me just show you the time evolution. Probably, I don't know how well you see it, but you can see that in the beginning you had some couple of frequencies, but this is a three-dimensional flow, so it's fairly complicated. And very quickly you get the formation of smaller and smaller vortices, energy cascades, and you have a very complicated solution, which is what the numerical method is able to resolve, right? So in other words, if you, for instance, have you want to see a time. So what does this lead to? So you, for instance, this is a visualization now of the point-wise kinetic energy, I think, at each point. So you can see we start initially without any sort of details in the solution, just two Fourier modes. And then as time evolves, you see the appearance of more and more structures, more and more energetic eddies. And then you start seeing this sort of the emergence of turbulence, and finally all this turbulent energy is dissipated out and you get more or less some decaying flow. So this is a very rich sort of a, and in some sense very pretty solution that is very nice to visualize. But of course, as I said, I have two hats that I wear. One is that of a person doing scientific computing, but the second one is that of a numerical analyst. And what is the role of a numerical analyst? It is really to rigorously study the error that we make when we are doing this approximation on a computer rather than solving it on paper, for instance, or what happens in nature. In other words, the question is that the error here, let's say, among other sources, is essentially dominated by the number of modes onto which you're projecting. But the question is, what is the error that you're making? How does it vary as the number of modes increases? Does it converge to zero as the number of modes goes to infinity, and so on and so forth? So you have to rigorously study this discretization error, in particular with the expectation that as you do more and more approximation, more and more modes, you converge to the ground truth, which is the exact solution in this particular case. So how do we study this? We have to rigorously study the discretization error. But even before we do that, we want to sort of just visually see how for different number of Fourier modes, as you increase the number of Fourier modes, how the solution changes, right? And here is the visualization. Means I don't have the legend here, but this is at 64. So 64 cube modes, 128, 256, and 512. And you're again seeing, I think, the point-wise kinetic energy with the same scale somehow, or maybe it's a vorticity, one of these sort of visualizers. And what you see is that as we increase the number of modes, we get more and more structure, right? So this is, for instance, between 128 and 256, there are smaller and smaller eddies that come in, and between 256 and 512, there are even smaller eddies that come in. So just visually, this does not look like something that actually converges. And this is indeed verified, for instance, just by taking successive differences between them, just to see if this is a Cauchy sequence or not. And for instance, in L1 or L2, and you see that this is more or less a flat line. So even if you refine, you're not getting any convergence, at least visually, right? Or quantitatively in this particular mode. So this is not very good, right? Because essentially the whole premise, the whole foundation of a numerical method is that as you refine, you should have convergence. But at least for this particular flow, you don't have convergence. But the question is this generic, or is this one particular example that I just plucked out to show this to you? So let me give you another example. This is a very interesting one. It's you know, in 2D, we have all these shear layers that are whose dynamics one likes to study. This is somehow an equivalent version in 3D. So you have a cylinder, which is written, this is the vorticity. So you have a cylinder and all the vorticity is concentrated on the cylinder. And then there's some shear. So the cylinder is being disturbed on with the velocity field. And then there is some evolution of the flow. So again, I take the same thing. I take this initial condition. It's the same box, periodic boundary conditions. And then the same method, spectral viscosity method. And what I'm going to do is to run the same algorithm again, right? And let's see what happens. So here, this is the picture. So in the beginning, you have this cylinder essentially. And then what happens to the vorticity as time evolves? As you can see, it becomes, it's very beautiful to look at. But as you can see, again, smaller and smaller structures are formed and it sort of starts filling up the whole space. This is the sort of visualization. And if I let it continue, you will see the same behavior going in, that large structures are broken down into smaller and smaller structures, which is sort of the essence in some sense of turbulence. But again, that's not my question here. My question is what happens as I refine the mesh, right? And as you would have expected, it's exactly the same behavior. So if you start with 64 cubed number of Fourier modes, and then you go to 128, there's a vorticity. You see that there are smaller and smaller structures. And when you go to 256, even smaller, and then this goes on, right? Of course, we have finite amounts of compute, so we can't really see more than this. So these two examples show that there doesn't seem to be any convergence on mesh refinement. But you can argue, what about other fluids? And you're only stopping at 256, 512. Perhaps I see convergence when I'm at, I don't know, 10,000 points or whatever. So let's try to even investigate that. So here is a slightly different equation, 2D, so we can do more computation. And these are the so-called compressible Euler equations. Again, probably you'll see them in the workshop. And we will do something. Now, this is the density. It's no longer the velocity field alone. This is the density. It's compressible. The flow is compressible. Density changes with time. And what you see is exactly the same thing, but in 2D. So you have a shear layer here. As you can see, the velocity field points in opposite directions. And then now it's no longer periodic, the flow. So what we are going to do is we are going to use a finite volume method, not a spectral method. But that's just a detail, right? And now let's try to do the same experiment. As we increase the resolution, what happens to convergence? So this is on 128 squared. You can see that some large vortices are being excited. It's easier to visualize in 2D than in 3D. 256 squared, the location changes, smaller vortices come in. 512 squared, you see even smaller and smaller vortices. Then 1024 squared, really, really smaller vortices. But since this is 2D, we can take almost infinite resolution, not infinite, but quite a lot of resolution. And this is what happens at 16,384 squared. So there's a lot of compute, but we just wanted to do it. And you see that there is no convergence visually, and smaller structures. These fingers come in, the vortices become smaller and smaller. A lot of interesting stuff happens, right? So in particular, when you take these successive differences, it's no longer, it's just a flat line, and it's a flat line for an order of magnitude refinement in mesh resolution. So there is no convergence, at least visually, at least empirically, right? And this is what is sort of generic. It's really generic. You take any reasonable flow, and this is what only in special cases where you have smooth solutions, you don't have this behavior. Otherwise, this seems to be rather generic. One can argue that you have not ruled out very slow convergence, like what if there's a log-log somewhere, right? But it's sort of, this is not going to be practically useful. It means even in the foreseeable future, you won't be able to compute at these resolutions that I just showed you. So it will be useless anyway. And we argue that this kind of lack of convergence is sort of reflected, or is reflective rather, is a manifestation of some deeper issues that happen with fluid equations. And this is what you're going to hear a lot about, means particularly with Camillo and Laszlo being in the workshop, that we know that entropy solutions are admissible weak solutions. There's no global existence for these things in 3D. So you cannot expect to prove convergence results. And we also know that these are not unique, and there are all kinds of instabilities and so on. So in that sense, if you try to do numerical analysis with the equations of fluid dynamics, then you reach a dead end pretty quickly. So how do we get out of this dead end? One thing that we can do is to think about a different notion of solutions. Rather than just trying to hammer down on weak solutions, entropy solutions, admissible measure value, admissible weak solutions, and so on, we try to do something else and look for a different notion of solutions. And this is where sort of my main point is going to be. And this is somehow essentially goes back to some extent to Erdos, or perhaps even before that, that whenever you're stuck with a sort of a deterministic problem, you make it stochastic, or you essentially randomize the deterministic problem. There's a long quote here, but the punchline is that randomize the deterministic problem. So empirically, how do we do that? It's very simple to do that. So remember this 2D experiment. That's why it's sort of easy to explain. So this is one particular initial condition, but no one stops me from making tiny little perturbations, and instead of running one experiment, to run several, an ensemble as we call it, right? So tiny perturbations. So even if these tiny perturbations are there, it shouldn't really matter. Means the size of the perturbations is very small, so the solution should be somehow close to each other. That's the idea, right? But let's see. So what we do is remember that when I just take one particular initial condition, then this is how the picture is. These are three different resolutions, and we don't get any convergence whatsoever. Now, what I do is that I take 2 or 6 or 8 of them and make these tiny little perturbations, and then I run the algorithm that I had before. But now what I do is I average them, right? I take the ensemble average. And if I take the 2 of them, I take 2 of these tiny perturbations and then average them. Already you see that there's no convergence per se, but you see that some features get averaged out, which is good news. When I take 8 of them, again, there is no convergence per se, but there's only 8 of these. But you can start seeing that some of these small scale features are swept out and there is a well-behaved average. And finally, when I go towards more of them, like 64, you start seeing some convergence. There's just the ensemble average, and you see that there is this is much better behaved. And when you go to 1024 of these tiny, tiny little ensembles, you have perfect convergence of the mean, and this is a much, much better behaved quantity, right? So in other words, what does this little experiment tell us? So what this little experiment tells us is that even though each of these individual realizations in some sense, so you have a initial condition and then you do this numerical simulation of this initial condition, that need not necessarily converge because of this presence of structures at smaller and smaller and smaller scales. Statistical quantities are much better behaved, which is probably not unexpected from a chaotic system, right? This is the basis of chaotic dynamical systems, that statistical quantities are very, very well behaved. But then the question arises is that how do you put them into a mathematical framework? Means this is not really just searching for an invariant measure, because we are not that interested in steady states, or global equilibrium states. What we are interested in also dynamics of transitions and so on. So how do you do that? Well, there are various options. Perhaps the sort of low-key one, and the first one that comes to mind was due to Ron DePerna in the 1980s, and this is the notion of measure-valued solutions, which in turn goes before that to Young and Tartar and so on and so on. So the idea is that what you have as the mathematical object, the underlying mathematical object, are Young measures. So these are, as all of you know, I think, space-time parameterized probability measures. These are limits of bounded functions, weak limits of bounded functions. So just intuitively, what happens is that if you have a weak solution or a strong solution, this is X, let's say one-dimensional, and at each point, there is a unique value which is associated with it. Whereas with a measure-valued solution, you take a point, and instead of having a unique value that is associated with it, there's a whole set of values, and what you have been given is a probability measure, what is called a point PDF on this set of values. So instead of saying that there's exactly one point or one value, you have value, one of these values with a certain probability, another value with certain probability, and so on. In particular, if the probability measure is Dirac measure at each point, then you get back to your classical notion of solutions, classical notion of functions. So instead of looking at, remember this, right? That at each point, we have a point probability density function. So we have to reinterpret our mathematical interpretation of the equations accordingly. And this is already done back in the day by DePerna and Mishra and so on. And I just illustrate this because it's easy to write down things for systems of conservation laws, which are, for instance, the compressible Euler equations. So all that you do is that instead of looking at the weak solution, what you do is you look at the action of the Young measure. At each point, there is this probability density function also in time. And then you look at the action of the Young measure on the identity, the action of the Young measure on the flux, and then you have some initial conditions of the Young measure, typically a Dirac mass, but need not necessarily be the case. And then the entropy condition or the energy condition is satisfied by some inequality. All these, of course, hold in the sense of distributions, needless to say that. So it turns out that the algorithm that I just showed you, where we take these tiny, tiny little perturbations and just average them, it's called an ensemble Monte Carlo algorithm. We can show, we can prove, and this was done many, many years ago, we can prove essentially that whether for the compressible Euler equations or the incompressible Euler equations, that this will converge on mesh refinement to something, to the measure-valued solution. So in some sense, the computation that I showed you is well-defined in that particular sense, and you can realize everything in terms of a measure-valued solution. And the reason is precisely because instead of just doing an averaging in space-time, which is what you do with weak solutions, you do an averaging in the ensemble, and the ensemble is much, much better behaved. So this is the basic idea. Unfortunately, and I think you might have guessed this, that these solutions, they're not necessarily unique. There are some weak strong uniqueness results, for instance, by De Lellis and Zekilahidi and Brenier, and by others also, DePerna, probably to some extent long before. What they do is, as long as you have a classical solution, Lifshitz continuous solution, then of course there is uniqueness. Otherwise, there is no uniqueness. And you can see this very nicely even with the Burgers equation in 1D. Means it's that even if, so now it's really a Young measure instead of just having an atomic data, because if it's atomic, it's entropy solutions and they're unique. But if it's non-atomic, like here, so it's exactly the same initial data at a point, is exactly the same final solution at a point, but in between you can do two different things and you can recover the solution. So it's totally non-unique. So it's in that sense useless. And the reason why it is non-unique is also very easy to explain. Because what the entropy solutions does, or sorry, measure value solutions does, is that it gives you an equation for the mean. So it provides some equation for the mean, but and maybe some bounds on the second moment because of the entropy condition or the admissible energy condition. But that's about it. So you have some conditions in the mean and the standard deviation, and you want to determine the whole measure. That's, of course, as we know, is not really possible. It doesn't specify the full measure. If you wanted to find out all the higher moments, you take a test function, you test with the equation. The calculation is a very simple one, even for a scalar conservation law. What you find is that this chain doesn't work. So even just to define higher moments or to define the evolution equation for higher moments, what you end up are with expressions like this. So essentially, the probability not just at that point, but at neighboring points. So essentially 2-point correlations come in. So in order to define higher moments at a given point, you need information about correlations at two different points. And you can continue this, right? So you can try to write down an equation for what happens at 2 points, because that's the quantity that shows up here. Then you'll end up, because of the nonlinearity, you will end up looking at 3 points and then at 4 points and so on and so forth. So this is a chain that you essentially cannot close, some sort of a moment closure problem. So if you want to work just with Young measures, then you cannot work with just pointwise Young measures. You have to involve high order correlations, even high order correlations and so on. So at the end of the day, essentially to have any chance of having a theory here, or even computation, what you need is not just 1-point PDFs, but what happens at two different points, 2-point correlations, 3-point correlations, 4-point correlations, and so on. And this was sort of formalized in some mathematical sense in this paper quite a while back. It was published in 2017, but it was written in 2015 or something like that. So these are called correlation measures. It's a detail, but essentially these are multi-point Young measures. Okay, so instead of having Young measures at just 1 point, you have Young measures at all possible points. It's like an hierarchy, right? So you have Young measures at all possible points. You need some control on small scales. And the main point of that paper was that these objects, these correlation measures, which are essentially multi-point Young measures, they are totally related, or they're identical to another very familiar object, which is a probability measure on functions. So in other words, you can think of it like this. I can take, for some object, I can take 1-point measures, 2-point correlation measures, 3-point correlation measures, 4-point correlation measures, this entire hierarchy, and I can compress it. I can say that it's equivalent to one object, which is a probability measure, but on functions. So how do you think of it? The interpretation is very straightforward. So you have all these functions visualized with different colors here. And instead of looking at a probability at different points, or 2 points, or 3 points, and so on, you say, okay, what's the probability for this green function, green shaded function to be there? What's the probability for the yellow one, and so on and so forth. So mathematically, it's not a big deal to look at a probability measure on a function space. You'll see that it leads to its own problems, but these two things are completely related to each other. So you can completely define probability measure on functions by just working out the correlations. So this is probably is not trivial, but it's not unexpected. So with these sort of frameworks in mind, one can define what are called statistical solutions. We were not the first to define them. These were defined by Foyash and Prodi and Temam and so on. But they defined it straight in the language of probability measures on functions. We came from the other side and we defined them in terms of the probability measures on these correlations, right? And we also showed that these are equivalent and so on. So essentially what you need to do is to write down the equations for all possible moments, right? So for instance, to write down for the second moment, I just take the scalar conservation law because this is easy to calculate. So these are the correlations between two different points. So you just do the math, you just do the calculation formally, and you end up with this sort of extended equation that is there. And of course, you can reinterpret it for arbitrary measures in the language of Young measures, and you get an equation like this. And then, of course, you interpret it in the sense of distributions. I mean, this goes without saying. So essentially, what does it say? That for any moment, there is an evolution equation that you can write down. Unfortunately, it's not closed, right? Because second moments require third moments require fourth moments, and so on and so forth. So for those who know statistical mechanics, the infinite dimensional version is giving you a Wheel equation, which cannot be written down by hand. But there's something called a BBJKY hierarchy, which is essentially these equations. For Navier-Stokes, these are also called Friedman-Keller equations, but they've been out for a while. So for me, statistical solutions are two things. First of all, they're probability measures on function spaces. This could be L1 or L2, depending on the context that you're in. And these are parameterized by time. So they start with some initial time. And then the evolution continues. And the point is that the evolution has to satisfy, or the moments of this, the correlation measures, these guys here, they have to satisfy this infinite family of equations. So you can write down an equation for statistical solutions. The question is multifold. What do you gain by doing this? And from my perspective, can we even compute these objects? These are sort of probability measures on function spaces. How are we going to go about it? So let me focus on the computational aspect. And if I have time, I'll come to whatever theoretical points can be made later. So first of all, just to explain in terms of the familiar concepts. So as long as you have a Dirac, so this measure on function spaces is a Dirac measure that is concentrated on a single function, then of course it reduces to our familiar notion of weak solutions or classical solutions and so on. In addition, what's the relationship with Young measures, right? So the first marginal of this is precisely the Young measure. This is the Debayan style measure valued solution. What is the addition is all these multi-point correlations, right? So in that sense, it has a lot more information. It contains a lot more information, this concept, than it was just a measure valued solution. So ideally, one would be able to prove more sort of stringent things about it. It's another question that we haven't succeeded, but this is certainly the idea that this object carries a lot of information. And this is sort of the main point. But now let me tell you that this is not some abstract object that is inaccessible. In fact, you can compute it. So let me see how can we compute them. Essentially, exactly the same algorithm as before, this ensemble Monte Carlo algorithm. So what do we do? Just like what we did before, let me just explain it with a 3D example. So we have some probability measure. It could also be a Dirac measure. Then we have to disturb it a little bit. So we have a probability measure on functions, which is different. When you draw from it, you lead to different initial conditions. You take any of these initial conditions, use your numerical method, let's say spectral viscosity method, then you end up with a solution like this, you end up with a solution like this. And these are the samples for this particular object. So you can form what is called the empirical measure, which is right here. And this is an approximation to the statistical solution, and we want to pass to the limit. But our limit has two sort of axes, right? One is the number of samples, because it is an empirical measure. This m has to go to infinity. And the second, of course, is delta, your discretization parameter. That has to go to 0. So in the limit is where we would like to realize the statistical solution. But it's exactly the same algorithm with which we are computing the measure valued solution. We just reinterpreted it for our needs. So as soon as you have this algorithm, the first question is, under what conditions will it converge? Because remember that when we had just Diracs on both sides, this was not converging, at least empirically, right? So is this any better? So of course, we don't have a theorem which says that it always converges. There are some conditions, and let me explain some of the conditions. So essentially what you need are some bounds, right? This is analysis, so you need some bounds. And the minimal bound that you always have is from some entropy condition or some energy inequality. So you have some LP bounds. And then the key point is this two-level correlation function, which is given in terms of the so-called structure function. Now, for those who know turbulence theory, structure function plays a very important role. Essentially, it tells you how correlations behave at small scales. That's all that it tells you. So the theorem, this is not one paper, but it's an aggregate of maybe 2 or 3 papers, is the following, that as long as the structure function has some let's say scaling behavior, it goes to 0 essentially. It need not have any power, but as long as it goes to 0, you have some consistency of correlation at small scales, and you have some bounds. That's enough to guarantee convergence, right? So for Young measures, this was enough. Just some bounds is enough. These are weak limits, so you can get them. But here we need some more compactness. And that compactness is provided by this sort of small scale information, which, for instance, could come from some Holder regularity, perhaps, or from some other conditions. I'll explain a little bit about that. But once you have these conditions, a sufficient condition for convergence is given by this. And there is some appropriate topology here. It's a weak topology on probability measures, and then you have convergence. So as long as these two conditions are satisfied, but this is where the challenge is, right? To show that these two conditions are satisfied more or less for free from the energy inequality or the entropy inequality, you can show an uniform bound. So the first bound here, the energy bound, you can easily derive it. That's straightforward. And usually because of the numerical viscosity, stabilization, and so on, we have what are called weak PV bounds. This is sort of outdated in this context, but it essentially tells you that at small scales, so this here, the energy bounds, controls the large scales. Things can't blow up in an appropriate norm. At the small scales, you always have some numerical stabilization, some mechanism by which you control the small scales. And these are given by these kind of bounds. The structure function has some nice behavior. The problem is, how do you match the two, right? This is where the additional compactness is really necessary at intermediate scales. And we don't have a sort of a global theorem which says that, you have some control globally. That's not available yet. What you have, of course, are you can make some intelligent hypotheses. And one of the hypotheses that you can make is that the scale separation, or there is some scaling in these problems. This is the sense or the basis of what Kolmogorov came up with, which is that there is some scaling or scale invariance in turbulent fluid flows, for instance. So our sort of assumption here is that there is some notion of scaling, that you can somehow marry the small scale with the large scale through the intermediate scales. And if that is the case, then of course the structure, you have control on the structure function, you have the compactness, and that leads to convergence. So essentially you have to check whether the scaling property is satisfied or whether the structure function has some nice decay. If you have that, then you can numerically at least verify that there is convergence. This can also be translated because the structure function and the spectra, they are sort of the Fourier transform is the spectrum. And this can be translated in terms of the spectrum, which is how Kolmogorov formulated his theory. So what Kolmogorov said is that turbulent flows, they have the scaling properties, they have some isotropy, homogeneity, and so on and so forth. Those are not important for us. What's really important is the scaling properties. We, of course, take the most general mathematical statement possible. And that general mathematical statement is that you have a spectrum, power spectrum of your total energy, kinetic energy, which is given here. And this power spectrum has to decay. It doesn't have to decay at any rate, but it just has to decay. In other words, you have what is called an inertial range, because this is what we are looking for in this intermediate scales. So if you say that your spectrum, so let me show you this. If you say that your spectrum decays, then when I multiply with this decay parameter, you should essentially get a bound. You don't need it to be constant, but you just need a bound. And once you have a bound, then the theorem applies and you have convergence. So essentially, with a weaker version of Kolmogorov's hypothesis of turbulent flows, we can show that that things converge, the numerical method converges. Of course, we cannot prove a priori that these hypotheses are satisfied in general, right? So we have to somehow verify it. So that's where the gap really lies, the theoretical gap really lies. But from a numerical analyst perspective, or from someone doing computational mathematics, is not an issue. I can always verify these conditions. So this is where the statement in terms of convergence is. But once you have verified, or once you have these objects, then of course you are in a very good shape, because you can show that many things converge. All multi-point statistics converge, because in this topology, all multi-point statistics converge, which mean that not just the mean or the variance or point PDEs, but the spectra, structure functions, multi-point correlation functions, all of them should converge on mesh refinement and on sample augmentation. And this is if this is true, this is very striking, remember, because I showed you that any deterministic quantity that you took was not converging. But now what I'm saying is that all statistical quantities are going to converge if these conditions are satisfied. But the question is, are these conditions satisfied? Can we check them at least, right? Let's start with the problem that we started out with, which is the Taylor-Green vortex. If you remember that deterministically, there was no convergence whatsoever. Now let's check if the spectrum or the structure function has these scaling properties. We can compute them. Remember that this was the picture that I started out with. All that I need is a bound. And in fact, you get better than a bound, perhaps not unexpected, different times here. And then you see for different kinds of resolutions, all the way up to 512, you can see that with some exponents, it's very nicely bounded. In other words, that this shows us that numerically, at least, we can go further. Means I think we have checked up to 2048 cube, but this was not a big deal. It was always remaining bounded. The spectra was decaying more or less uniformly. And this tells us that we can apply the theorem now. We can't prove this, but we verify it. And then we have the theorem which tells us that there is convergence. And you actually see that, right? So this was sort of the deterministic mesh refinement. This is the mean, as you can see already. I mean, these are different visualizations. As you can see, as we refine, the mean converges, even the variance converges very, very nicely. So indeed, these conditions are satisfied, and then they imply convergence, right? And in fact, you can go further because essentially the topology that we have is not a strong topology, it's some weak topology. So we cannot prove that under some Wasserstein distance, for instance, on measures, there's convergence, but we actually observe very nice convergence. So in the left panel here is different times, of course, but this is the first marginal. It's impossible to compute the Wasserstein distance between two measures in infinite dimensions. That's simply not possible. But we have this hierarchy, right? So we can take 1-point marginals, compare them, 2-point marginals, compare them, 3-point, 4-point. At some level on a computer, you can only do so much. I think in 2D, we have up to 4 points, very, very expensive computations. In 3D, only 2 points. So this is a 1-point marginal. This is a 2-point correlation marginal, 2-point correlations, but they converge very, very nicely. For instance, even here, as you can see, there is very, very neat convergence. So what it hints is a stronger convergence than what we were even able to check with the theorem and the empirical verification that I just showed you. So these flows are not badly behaved at all statistically. More about that later. So this was one example. What about the cylindrical shear flow? This other example that I showed you, which is generating all these tiny looping vortex tubes and so on. When you take the mean and the variance, all these large scale features are swept out. You have a lot of averaging happening and you get this very, very nicely behaving. This is with respect to time. Okay. You have very, very nice behavior in some sense, and you sort of cross check that. The spectrum is very nicely converging, as you can see, or it's at least bounded. So the empirical conditions are satisfied, the theorem applies. And again, if I take the Wasserstein distance, it's very, very neat convergence, slow. The exponents are like, at least for the second order marginal, it's like 0.25, 1/4. For the first order, it's minus 0.4. So it's very, very nice convergence. So in general, and this we have verified for compressible flows in 2D, 3D, incompressible flows in 2D, 3D with forcing and so on and so forth. So all that I'm saying is that we haven't encountered a single situation where there is no statistical convergence. There always is nice behavior, nice statistical convergence, even if deterministically these things are very, very badly behaved. So this is the sort of point that I'm trying to make. So now we can do these kind of computations, but and we know that these computations are very well behaved, but can we sort of probe the system, gauge the system to learn something interesting about it? So there are many, many different properties that one can test in this test bed. But let me focus on one property, I think, which is, at least to me, of fundamental interest. And in nature, stability is what is really necessary. Okay, so you have some notion here, statistical solutions. The question is how stable they are, in particular to perturbations, right? So if I make tiny, tiny changes, how much does it change? So what I do now is that I'm going to change. So remember that I started out with something, I made these tiny, tiny perturbations, and then I let the amplitude of perturbations go to 0. That's the first step that I want to do. And I want to see whether there is stability in this limit or not, right? So the limit of, let's say, perturbation being 0 or small perturbation limit. And in that case, so now this is how the perturbation changes. We have the computations. This is the first marginal. No, this is the first marginal. This is the second marginal. And again, you see very nice convergence as the limit is reached. So in other words, even if, so they are stable with respect, at least to small perturbations, and you'll see large perturbations in a minute, but they're very, very stable to small perturbations. As you can observe, for instance, these ones, they converge very, very nicely. So no issues when it comes to the stability with respect to amplitude of perturbations, but you can go further. What you can do is that I made these perturbations with some uniform distribution. I can change that completely. I can say, okay, let me use Gaussians instead. and compare between the uniform and the Gaussian. As long as the size of the perturbation is small, these things should be close to each other. And this is very nicely verified here. This is the stability to perturbation type. As you can see, again, there is some very nice behavior. These things converge as the perturbation is reached. So what it tells us is that there is some universality in the sense that as you make small perturbations, things are stable, right? And in fact, you can go even further and try to test, because essentially these are trajectories, right? For deterministic solutions, this would be trajectories in function space, but now these are trajectories in some very badly behaved measure space in infinite dimensions. But nevertheless, we can at least empirically see how the stability behaves as a function of time and as a function of distance. So many things to unpack here. Let me just, this is not published, it's very recent work, but it's, I think, very interesting. So on top here is, I do some computations, but this is deterministic. For very, delta is very small, but it's deterministic. I know there is no convergence, but I want to see how the finite dimensional projected dynamical system, how unstable it is, right? Essentially, that's the basic idea. And for that, I want to compute some separation of trajectories, right? So I start with some initial perturbations and see how these perturbations grow in time. So, or the norm of these perturbations grows in time. Of course, they can't completely separate because we have L2 bound. So they have to fill up some ball in L2, but how do they separate at least initially? So there are two things with respect to which we measure the stability. First is the behavior of this distance in time. And second, how does it vary as a function of the distance? So that's the basic idea. And in both cases, for the deterministic solution, it's at least exponential. I think it's double exponential, but it's very difficult to do that numerically. And this is also, there is some theory about it and so on. But you observe a very nice exponential divergence. So small perturbations is really chaotic. Small perturbations, they both in distance as well as in time, they grow exponentially large. Okay, till they are bounded by something. So this is verified here. Now I want to ask the same question statistically. So now I don't have a function anymore, but I have a measure. It could be a Dirac measure, but I know that it becomes non-atomic as the flow evolves. But I want to measure, for instance, the Wasserstein distance, one Wasserstein distance. I'm sorry, here I missed the one. And then see whether these trajectories, they are exponentially diverging or not, right? So we would expect that because of this, if it was deterministic, it would go exponentially far away. But because of this nice behavior statistically, what we observe, and these are just observations, there's no theory here, is something very, very interesting, that both in terms of the time, the growth over time, and the growth with respect to the distance, it is not exponential. It's far from it. It's a power law, and with exponents that are it's less than a square root. It's only sublinear. So there is separation which is happening at scales which are sublinear. Some means there's no universality as such, but I don't know if you can read it. So here it's like 1/3, 1/4, 1/5, and so on, means half. So there are different kinds of exponents which are coming in. So in other words, instead of having exponential separation, statistically, what we observe is a power law separation. There is a separation, means this is some flow. There is separation, but a power law separation, which there's no universality in the exponents. We're still doing experiments to understand how these things are related, but far better behavior. Just to prove something like this would be, or at least even to come up with a precise, crisp hypothesis would be very nice. And it's only enabled because of all this computational infrastructure that we have been able to build. And this tells us that statistically, these things are not badly behaved. If this were true, right? Just imagine, statistically, just imagine this is a half and this is a third. And there's not a huge separation of trajectories. These are inherently much more stable than a generic solution of a PDE would be, right? So this would be a very, very strong statement. But these are just preliminary results, but they indicate that this kind of a functional relationship is very much true. And there is power law separation instead of exponential separation, and these power laws are sublinear. So this is the main message that we have observed so far. Okay, so let me switch gears, because I said that I'll talk a little bit more about computation. And what's the cost? Means what's the issue here? How do I compute these things? I showed you all these nice properties, this convergence and so on, but this comes at a cost. Means, for instance, we had a machine here in Switzerland, a very, very powerful machine. It was called Daint. We have a code which can access this machine, which can use it. It's run on GPUs. And for a single simulation at very high resolution, 1024 cubed, it took us about 100 GPU hours, means 100 GPUs running in parallel for 1 hour. And this is a huge change compared to what we had before. So when I was a PhD student in Bangalore, we didn't have GPUs. GPUs were just about starting. We had CPUs and very slow ones. But even with the fastest CPUs, this is a factor of 50 less. So if I just had a code which used CPUs, then I would not be able to even do this exploration that I just showed you, right? So there's a factor of 50 speed up that we got from GPUs. But because we have, so this is a convergence with respect to number of samples, right? This is Monte Carlo. So both theoretically as well as empirically, it's square root. So you need many, many samples in order to get a good answer. So at least 1,000 samples is a basic requirement in order to get anything. And then the cost adds up because it's 94 times 1,000, which is 94,000. And then it gets expensive. Switzerland is a very expensive country, but all over the world, it's an expensive simulation, $500,000, 500,000 Swiss francs, and so on. And this is unaffordable. I think I gave a talk at in Bangalore some years ago where I said, this is the challenge. It's sort of, we cannot afford these kind of big computations, and you need to bring it down by a factor of 50. So the factor of 5 comes down simply because there's a new system which is coming up. It's another very powerful supercomputer full of GPUs and so on. So just by using that, just by running the same code on that new system, we got down from 94 to 21. So we got factor of 5 more or less because computers become cheaper. But there's still a factor of 10 which is missing. And without that factor of 10, it's still these computations are not going to work out. So you need fast computations in some sense. So these days means all of you know that we live in the age of AI. Can we somehow leverage that? Can we leverage machine learning for this purpose? And machine learning is all about three things. You have a lot of compute, a lot of GPUs. That's why this new machine is for AI applications rather than for traditional physics simulations. You need lots of data. Well, we have some data because turbulent flows generate a lot of data. And then there are these mathematical objects, deep neural networks, which do this magical work, right? And in particular, because we are in an infinite dimensional setting, we work with what is called operator learning, where input and outputs are functions. I'm not going to give you the details here, but the question is, can this come to the rescue? Can it significantly reduce the computational time from the ones that we already have? The answer is unfortunately not in this case, right? So here is, of course, Taylor green vortex. This is again visualized through the kinetic energy pointwise. Remember this plot here. And I take really a state-of-the-art, what is called neural operator, one a state-of-the-art neural network algorithm for these purposes, something which combines Fourier and physical convolutions together. The details are not important. And what you see here is the same picture. First of all, you don't see any variation across samples. Whereas here, there is quite a bit of variation as the same is a statistical solution. So these are just samples. So here you generate the same thing. And you see that the details are simply not there. This is not able to capture these kind of very, very fine details that turbulent flows have. If you look at the variance, these are, as I said, statistical quantities are well behaved. These are different initial conditions, but the variance is very similar. But again, it does not generate the variance that we need because all the variance is at the small scales. So this is where these methods, these traditional, so not traditional, these have been developed in the last year or two, but they were not good enough. So what you do here is that one has to go back. I think all of you know about Sora. This is this video generator that OpenAI had, and also image generation. And it turns out that the engine behind this is something called diffusion models. And this is what we are going to repurpose for our needs. And this is something very, very interesting. So let me tell you in 1 minute what a diffusion model is, because it's really ingenious. So what diffusion, remember, the idea is that you're going to sample from a distribution, from a probability distribution. Could be very, very high dimensional, for us, essentially infinite dimensional, right? So how does a diffusion model do this? What it does is the following. It's very, very clever. So there are two steps to it. So one is a noise addition process. So let's say that this is a sample from my distribution. Okay, statistical solutions. This is a cylindrical sea of flow. This is a sample from my distribution. What I do is I look at these forward arrows. I add noise. Okay, so I add noise. So in the beginning, I have this amount of noise, then more noise, then more noise, and finally it becomes a Gaussian. So I just keep on adding noise. This is what is called a forward step. And this is essentially you have to solve a stochastic differential equation, which is given here. And then you add noise. Okay, so you add noise, so what? But now it's a reverse step that is interesting, right? Because what you do is that in order to find a new sample, my input would be this noise, essentially Gaussian. So I can always generate a Gaussian distribution. Perhaps I give the initial conditions. That's why it's called conditional diffusion. And then what I'm going to do is I'm going to solve. So this STE is reversible. It's called a reverse STE. So it can be solved backward in time somehow. And from this, you generate the sample again. So first you noise, and then you take the noise, and then you denoise, right? And you just use the fact that the STE has a reversible flow. And this is sort of the basic idea. So in both steps, you solve an STE. But the reverse STE, it requires something called the score function, which is given here. It's sort of, maybe I did make a mistake because there should be a log here. So it's essentially the log of the probability distribution. That's the score function from statistics. But this is not available. We don't know the probability distribution analytically or even numerically. Right? At best, we can sample from it. So this is where the ingenuity of the ML people comes in, because they found out a smart way to find this score function. And the way it is done is during training, and this is the neural networks that we train from data. What you do essentially, and this is beautiful, is that you start with the initial condition, because we condition our previous time step, we condition our measure to reflect that. And then you start with some clean sample and a noisy sample. So you give the noisy and the initial condition in, and then during training, you also know what is the clean sample because you have added the noise, right? And all that you do is to get the neural network, train the neural network, change the neural network parameters so that you recover the clean samples. And there is a formula, very well-known formula in STEs called Tweedy's formula, which tells you that doing this precisely gives you the score function. So this is sort of ingenious idea. So first, at the level of training, you have some data, like the data that I generated from the probability distribution or from a related probability distribution. I add noise, for instance, by the forward STE, and then I train my neural network to solve or to denoise it, right? To solve that, denoise it. So this is, there are some details, and this is a very sophisticated neural network that does the job here. I don't need to give you the details, but let's say that the neural network, each time it sees a noisy sample, and the thing that it's conditioned on, it provides you a clean sample. And that is the score function. So you use that while solving the STE. So this is where you plug that in. You solve the STE backward in time, and then you recover, you get samples. So at inference, what you do is that you start with Gaussian and you end up with samples. And this is, it can work in any dimensions essentially, and so on and so forth. So it's a very attractive thing for us because we are essentially in infinite dimensions, but because we have numerical approximations, we can say very high dimensions, right? So even if we have 128 cubed, that's a million dimensions. So this is the level at which we have to operate. So what we did is that we took, of course, the people at OpenAI didn't do this. We had to do it. So we took these models, which are sort of state of the art in that sense. This is a joint project with people from Google Research. So we were able to use their expertise. And then we have our own algorithm. It's called a generative AI algorithm. So it will generate samples of the statistical solution, given the previous time step or given the initial conditions. So that's the basic idea. So does it work? Well, here is the proof of the pudding always lies in the eating. You see at the kinetic, so here is the ground truth. Okay, they just tell you there's 3 different samples of the ground truth. Here is what a state-of-the-art ML model was giving us, and here is what our new model gives us. You see? So remember that these are random samples. They shouldn't be identical. But it looks very similar. In fact, I have showed this to many, many people. If I don't tell them, they cannot distinguish between the AI-generated one and the physics-generated one. There is no way even experienced turbulent modelers have not been able to see this. And this is for the velocity field, because the kinetic energy is reflected in the velocity field. And all the training happens with the velocity. You know, it has never seen the vorticity. It has to infer it later. And this is how the vorticity looks like. Again, with the standard neural network, you don't get this thin vortex tubes, these loops, and so on. Whereas with this algorithm, it's almost indistinguishable to the eye from the ground truth, essentially, from the physics-based simulator. So this is able to learn this. And in fact, there are also quantitative results in terms of the Wasserstein metric and so on in the paper. Paper should be available. It's already finished. You know, we're just waiting for some permission from Google. But and in terms of the statistics, it does very well. Of course, the mean is approximated very well. But the key is the variance, right? Because this is the one that is new here. Because mean, also a deterministic simulation was able to do that before. But now in terms of the variance, it's almost exact. So it's able to generate the variance that the system has. And the reason is that it's able to generate rather than learn, but generate these small scale eddies that are there. You see it also in the 1-point PDFs, also in the 2-point ones. But let's pick a point here. And I don't know how well you see it, but like a deterministic ensemble-based approximator, neural operator, it just gives you a flat line. Yeah? Oh, sorry. There was some. Can you hear me? Yeah, I think there was some echo. But you see that the probability density function is approximated very, very well. And the reason why this works is precisely because of the nature of turbulent flows, the nature of spectra. So here is the same flow, Taylor Green in the beginning. So this is at t 0.8. Turbulence has not yet set in. And this is at t equal to 2, where the turbulence is developed, right? So this is the two differences. As you can see that in this so-called laminar regime, small scales, first of all, they decay much more, almost exponentially fast. They don't play a role in the global energy budget. And then, of course, the standard neural networks are able to catch up quite a bit. Whereas here, because of the nature of turbulence, more and more small scale information gets generated and it doesn't decay as fast. It's a power law decay. So as you can see, the spectrum moves up, and you can see how well this Gen CFT is the name of our algorithm, how it is able to generate this entire spectrum. And now, of course, at least at low resolutions, this was taking me about 10 seconds on a GPU, a little more, but let's say 10 seconds. This takes 1/10 of a second. So you get a factor of 100 speed up here. And also compared to a CPU, it's much more. So if this scales, then we have solved the problem that I mentioned like 5 years ago. So I'm very excited about this. So we can do these computations at large scale now. That is sort of done. But why does this model work? So in the same paper, we have some theorems and some toy models where we explain what goes on. So this is a very nice and I more or less finish with this. So what am I showing here? Lots of plots, but let's see. So I have a toy model here. It's just one dimensional. It's not infinite dimensional. So I have some mean, and then I add some oscillations. This is true for fluid flows. This is true for structures, material science, where you add microstructure and so on, molecular dynamics, whatever you name it. So I start adding some oscillations, and I keep on adding more and more oscillations. So of course, in the limit, there's no deterministic limit. You end up with a Young measure at each point, right? And this is, since it's 1D, that's the statistical solution in some sense. Now, if I use a deterministic machine learning model, I sort of feed it this kind of data, then for a few oscillations, it does very well. But if I have a lot of oscillations, then at least when it's not trained enough, it just directly goes to the mean flow. And there's a theorem, one can write down a formula in this particular case, which shows exactly this is what happens. Of course, if I train it a lot, I show it a lot of examples with lots and lots of oscillations, then it starts sort of adding some oscillations. As we would also add some oscillations, it starts adding some oscillations. But of course, if there are just too many, it again goes back to the mean, which is a local minimum, and then stops there. So this is how a sort of a deterministic machine learning model does. What a diffusion model, which is this stochastic or generative model, does is something completely different, and this is mind-blowing. So what it does is, if you have few oscillations, of course, it behaves like a deterministic model. But if you have many, not too many, but many, it starts by fitting a probability distribution, okay, because it's based on noise and denoise. So it starts by fitting a probability distribution. And then when you show it more and more samples, it sort of takes out some of the oscillations and reveals somehow the ground truth. But in case there are just too many oscillations, it stops there. And then that's a good enough answer for us, because anyway, it's an approximation to the probability distribution. So this is novel, this way of understanding diffusion models and how they work. This is novel, and this is sort of, it's all written in formulas in this paper. And this is why we observe what we observe here spectrally, as well as in terms of probability density functions. So in terms of computing, we have the compute now to do large scale computations. And now with these machine learning models, we can really get the cost down. Means it's sort of something that was unbelievable 20 years ago, to be able to do this in 1/10 of a second. This is just insane, to generate a 3D flow in 1/10 of a second. But theoretically, the advance is much less slow, right? So essentially, my point was that, and I'm finishing with this, that to compute fluids deterministically is impossible. I told you the issues that come in. So some stochasticity, some probabilistic framework, statistical solutions, I think are an attractive alternative. And what we can do is we can provide some verifiable convergence criteria. And once you verify it, there are theorems which tell us that, okay, it will converge, and we do observe this convergence. And the computational cost can really go down with, first of all, with more compute now, but also with diffusion models. And this is sort of the new thing That was, let's say, not there even 2 years ago, let alone 5 years ago. But of course, now once we have all this computational machinery, what we can do is we can investigate at scale empirically to discover probably new interesting properties. The one that I sort of hinted at was more about stability and regularity. There seems to be such properties available, but of course, there's no theory behind it. I think once these models or these properties are well established, some of you would be interested in trying to see if something can be proved, what can be proved, and so on. But the bottom line is fluids are much better behaved stochastically, statistically than they are deterministically. And this is what my talk was essentially trying to show you. So thank you very much for your attention.
Thank you, Siddharth, for your very nice talk. Are there any questions?
I can't hear anything.
Hi.
Hi. Yes.
Try this one. What about now? Can you hear me now?
Yes. Well.
Okay, great. So I have a question about the part of your talk when you were talking about this separation of trajectories.
Yes.
You said that you don't observe any universality, but I wonder how you can relate this to the classical picture of pair dispersion in turbulence, where, I mean, there is a power law, and let's say for 3D turbulence, it should be cubic. So,
yeah.
And of course, there's a different regime. There is a diffusion regime where the power law should be more like square root, which is one for diffusion. So, but because I didn't understand, you said that somehow it's surprising that you get a power law, whereas for deterministic, you would expect an exponential. Can you elaborate on this a little bit?
Okay, that's a good question. I was quick there, but yeah. So I don't know if it's surprising, but the point is that so universality is qualitative and quantitative, right? So first of all, we don't observe. Perhaps for Taylor Green, we observed the sort of spectra that Kolmogorov predicted, but some of the other flows which are not yet fully developed, perhaps, or which are not very isotropic, very anisotropic, and so on and so forth. There is not this, because these conditions were derived under a lot of assumptions, right? So in many of these flows, these assumptions are not necessarily satisfied. But my point is that the separation is not just about being exponential or polynomial, it's actually sublinear. So the exponents that you get, and this is not in a diffusion regime per se, right? This is in, well, this is, you see this is a function for time, and it starts with initial time, and then there is some separation and so on. So the all that I want to say is that whatever theory is out there or phenomenological theories out there, the exponents that we get in terms of the separation are different from them, and they are more sort of, let's say, optimistic than the theories are based on bounds after all, right? Means it's sort of, so that in that sense it makes sense. But again, as I said, this is very preliminary. One needs to understand, in particular, one needs to understand how the behavior of the structure function or the decay of the spectra is correlated, if at all, with these kind of separation of trajectories. But it is all that I'm saying at the moment is all the observations are that it's more optimistic than what the theory provides, which is perhaps not unexpected. After all, the theory provides only bounds, right? And this was sort of the main point. But I fully agree that this requires more investigation.
I have another question on the structure functions. You said that in the for the proof of convergence, you just need some decay.
Yeah.
But did you, in the numerical simulations, did you actually were you able to compute structure functions?
Yes. Yeah, all the time. I didn't show you any, but and also in the published papers, they're always computed all the time, and you get very, very neat structure functions. And it's not 1/3 always, but perhaps for Taylor Green it is 1/3, but it is thereabouts 0.4, 0.2, somewhere. And we computed not just the second order structure function, but also third order structure function, fourth order structure function, and so on and so forth.
Because I guess this is a simpler situation, so it might be interesting to compare to the all the work in statistically steady turbulence, where computing like fifth or sixth order in the usual HPC frameworks is already sort of very delicate.
This is fifth or sixth order is hard for us also, means it's sort of the compute is quite extensive. But maybe now with this sort of generative AI models, this will be straightforward, but it depends on how much do we trust it to be able to do those computations. But I see that we always compute the structure functions up to a certain order. And this is always there. So, and we expect to compute high order structure functions sooner rather than later. So it's of course an interesting question. I didn't show you any here because yeah, but I think you can already see that from the spectra. For instance, this one, you see that I can't see it very well, but it's minus 1.89 and minus 1.76. So of course the structure function is so it's you have to add whatever plus 1, so you can compute the exponents of the structure functions accordingly. So it is we always compute them. Yes.
Any other questions? Any other questions online? Thanks, Siddhartha, again.
Thank you very much and have a nice workshop. Bye-bye.
Thank you very much.